Good evening, scholars. Mr. Spears here. Tonight's lesson is about endo and exothermic reactions. To understand endo and exothermic reactions and why they happen, we must first discuss and define vocabulary used when explaining situations involving heat, temperature, and energy. First, the terms endothermic and exothermic are defined in part by the flow of energy or heat between a system and its surroundings. The system of a chemical reaction is the reactants and products of that reaction. Everything around the reaction is considered the surroundings. The picture on the right shows a double replacement reaction between aqueous solutions of lead-2 nitrate and potassium iodide. The yellow cloud that forms is insoluble lead-2 iodide, one of the products of this reaction, the other being aqueous potassium nitrate. The atoms and bonds of these reactants and products are the system of this reaction. The water of the aqueous solutions, the test tube that holds the reaction, as well as the air around the test tube serve as the surroundings for this reaction. Even the student that watches is considered part of the surroundings. A useful piece of information for students as they learn about endo and exothermic reactions is that thermometers are always part of the surroundings during a chemical reaction. Furthermore, the readings they provide always show the temperature changes in the surroundings. Indeed, much of what we know about a reaction itself is due to the temperature changes in its surroundings. Endo and exothermic reactions absorb and release energy due to the law of conservation of energy, which states, energy is neither created nor destroyed, it simply changes form. The cars in the animation move across the track as their potential energy is converted into kinetic energy and vice versa. As the cars climb to the top of a hill, they slow down as their kinetic energy is changed into potential energy. The cars pick up speed when they go down a hill as their potential energy is transformed into kinetic energy. When one form of energy decreases, the other form increases. Thus, the total amount of energy in the roller coaster is conserved. Chemical potential energy, or CPE, is the energy stored in the atoms and bonds of reactants and products. During a chemical reaction, this potential energy increases or decreases as it is changed into other forms of energy and vice versa. Some other terms to consider are heat and temperature. Heat is not energy per se. Instead, heat is the flow of energy between hot and cold objects, or between a system and surroundings. Energy can move back and forth between system and surroundings because of heat. Finally, we must remember that temperature is a measure of average kinetic energy. If we know what is happening to temperature in the surroundings, then we also know what is happening to kinetic energy. When magnesium metal reacted with hydrochloric acid during the endo and exothermic lab, we observed that the temperature in the surroundings, or in the styrofoam cup, increased. What caused this increase in temperature? The potential energy diagram of the reaction shown will help explain the story. First, the x-axis shows the progress of the reaction measured by time. The y-axis shows the chemical potential energy of the system. In order for this reaction to take place, the magnesium and the two hydrochloric acid molecules must collide with sufficient energy to break their bonds. The breaking of these bonds requires energy, specifically a positive 860 kilojoules per mole. The magnesium and the hydrochloric acid molecules can bump into each other over and over again, but if they don't collide with at least 860 kilojoules per mole of energy, their bonds will not break and the reaction will not begin. The positive sign indicates that the 860 kilojoules per mole of energy is put into the system. Thus, the breaking of bonds is endothermic. The energy required to break the bonds of the reactants and start the reaction is called the activation energy. The activation energy for a reaction is always the difference in energy between the reactants and the activated complex and is given the symbol EA. The activated complex is a short-lived, high-energy state where all the bonds of the reactants are broken and the new bonds of the products are ready to form. Almost immediately after the old bonds of the reactants break, the new bonds of the products form. If the breaking of bonds requires energy, then the forming of bonds releases it, as the hydrogen, magnesium, and chlorine atoms form the bonds of the products. A negative 1,250 kilojoules per mole of CPE is released, resulting in products that are lower in energy than their reactants. The forming of bonds is exothermic because energy is being released. When the energies during the bonds breaking step and the bonds forming step are compared, the sum of the two steps result in a net amount of 390 kilojoules per mole of energy released, as indicated by the negative sign. This net amount of energy also represents the difference in energy between the reactants and products, called the heat of reaction or the change in enthalpy, symbolized by delta H. The 390 kilojoules per mole of energy released is called the heat of reaction because it is not released until it flows out of the system in the form of heat. Reactions that release a net amount of heat are known as exothermic reactions. At this point, the flow of energy in the reaction is chemical potential energy in the system is transformed into heat released. Now we have the means to explain the rise of temperature we observed in the surroundings from this reaction. As the net 390 kilojoules per mole of energy leaves the reaction in the form of heat, it has only one place to go, the surroundings. When the heat enters the surroundings, it is transformed into kinetic energy as the particles there begin to move faster. The rise in kinetic energy results in a rise of temperature, as temperature is a measure of kinetic energy. The energy flow of this exothermic reaction is complete. Excess chemical potential energy in the system is converted into heat. This heat moves into the surroundings, where it is converted into kinetic energy. As the potential energy in the system goes down, the kinetic energy in the surroundings go up. And thus the total energy of the reaction is conserved, and the law of conservation of energy is obeyed. This table summarizes exothermic reactions. Before the reaction, the chemical potential energy of the reactants is high, while the kinetic energy of the surroundings is low. After the reaction, the chemical potential energy of the products is low because heat was released by the reaction. The heat was transformed into kinetic energy in the surroundings, causing the temperature to rise there. Remember, exothermic reactions always raise the temperature of their surroundings. Thus, exothermic reactions always feel warm. The second part of our lab saw baking soda mixed with vinegar. During the course of the reaction, we observed that the temperature in the surroundings decreased. Another reaction, but yet a different result. Again, a potential energy diagram will help us explain our observations. Just as in the reaction between magnesium and hydrochloric acid, the bonds of baking soda and vinegar must be broken. To break these bonds, an input of 1,430 kilojoules per mole of energy must be absorbed. Again, notice the positive sign. When this activation energy is absorbed, the activated complex forms. Again, notice that the activation energy is the difference in energy between the reactants and the activated complex. The reaction is not complete until the sodium, carbon, hydrogen, and oxygen atoms form the new bonds of the products. As new bonds form, 1,390 kilojoules per mole of energy is released, resulting in products that are higher in energy than the reactants. When the energies during the bonds breaking step and the bonds forming step are compared, the sum of the two steps results in a net amount of 40 kilojoules per mole of energy absorbed, as indicated by the positive sign. The positive delta H indicates that a net amount of heat flows into this reaction. Reactions that absorb a net amount of heat are known as endothermic reactions. As we follow the flow of energy during this reaction, we see that heat enters the system and is converted into chemical potential energy. Generally, endothermic reactions have higher activation energies when compared to exothermic reactions. As a result, endothermic reactions use much heat from their surroundings to help break their bonds. Because these reactions do not give back as much heat as they use, they leave their surroundings feeling cold. To produce the extra heat needed by endothermic reactions, kinetic energy in their surroundings decreases, causing the particles there to move more slowly. The decrease in kinetic energy is indicated by a drop in temperature. The kinetic energy is converted to heat and flows into the system, where it helps break the bonds of the reactants, and ultimately the sum of it is stored as chemical potential energy in the products. The energy flow of this endothermic reaction is now complete. Kinetic energy in the surroundings is transformed into heat. The heat flows into the system to help break the bonds of the reactants, and the sum of it is converted into chemical potential energy and stored in the products. This table helps organize the important details to know about endothermic reactions. Remember, endothermic reactions always lower the temperature of their surroundings. Thus, endothermic reactions always feel cold. Okay, that concludes tonight's lesson. I hope you have a better understanding of endo and exothermic reactions. If you have any questions, leave a comment or send a direct message to my YouTube channel. As for my students, write down any questions you may have and bring them to class. Thanks for watching and have a great day.